areas of the brain that you use. You just become more and more efficient in your use of these brain regions. So this suggests that there's abnormal specialization, but also that it requires tremendously more resources for the person with autism to process a face than a typical person. Now the question is, are we detecting here some kind of early genetic abnormality in the face processing system? And this could be the case. After all, as I said early on, you can see even in neonates this preference for tracking faces. So we know that the face processing system emerges really early in life. And so it's possible that what we're finding here is an early behavioral marker that's related to some sort of genetic abnormality. Now, on the other hand, it's possible that the difficulty lies somewhere else. And the difficulty results in the child with autism not being interested in faces. Faces are not rewarding for some reason. Whatever mechanism is in play that naturally draws our attention to faces is simply not working in autism. In this case, what might be going on is that the face processing system is simply not receiving the adequate kind of stimulation during early sensitive periods when we think these systems are coming online. So what we're looking at now at the University of Washington is whether an early intervention that specifically is targeting attention to faces and social interaction, whether children who respond to these interventions then go on to show more normal patterns of brain activity. Now, before I leave the brain imaging studies, I want to tell you about one other kind of study that's going on here at the university, and these are being conducted by Steve Dager and Seth Friedman. And they're using two different techniques. One, MRI, we've talked about, but in this case, they're using it to look at the detailed brain structure. And they're also using a technique called magnetic resonance spectroscopy, which allows us to look at brain chemistry. So here you can see a typical MRI where you can look in detail at both the gray and white matter of the brain. And Steve and Seth are following children longitudinally during early development to track the way the brain is developing. And they can also then look at chemicals, these three chemicals, choline, creatine, N-acetyl aspartate, and that are found specifically in neurons. Now, these chemicals resonate at specific frequencies in response to the magnet. And they provide for us a sensitive measure not only of cellular function, because these occur in the neurons themselves, but also a rough index of the density of the neurons. In fact, this measure is so sensitive that you will see changes in these chemicals in a person who's had the beginning of a stroke before you'll see it on a structural MRI. Now, so let me tell you a little bit about what Seth and Steve are finding using this in a longitudinal study of young children with autism from age 3 to 6. And the first question that they were interested in asking had to do with overall brain size. Because it turns out that one of the most well-replicated neuroanatomical findings in autism is a larger than normal brain. We knew from other studies that by elementary school age that for some reason children with autism have larger than normal brains, but we had no idea when this abnormal growth process began. So Steve and Seth were very interested in whether even at age 3 we would see this larger than normal brain, and indeed that is what they found. They found that children with autism by age 3 have larger brains than typically developing children, and also 3- and 4-year-old children matched on IQ who are developmentally delayed but do not have autism. Now, we know from looking at head circumference at birth that these children probably have normal brain size at birth, because it turns out that head circumference is a pretty good proxy for overall brain size at birth. So there appears to be some kind of postnatal abnormal brain growth process that's occurring that we still have very little understanding of. But one of the hypotheses is that perhaps this is due to an abnormal process of neuronal cell death. And let me explain that. It turns out that in normal brain development, our brains actually overproduce the number of neurons, and then through genetic mechanisms, they naturally die off, and we then have the number of neurons that we have as an adult. Similarly, it overproduces the number of synapses, and through both genetic and experiential mechanisms, these are reduced. So a 1-year-old actually has more synapses than we do. So one of the hypotheses was that perhaps what's going on here is that these children simply did not have the normal process of cell death, and so really what we have is more cells here. Now, if that were true, what you would predict when you look at those brain chemicals is that children with autism should have higher levels of those brain chemicals. But here's what Steve found. He actually found that the children with autism had lower levels of NAA and creatine and choline than children with typical development and delayed development. So we think that the hypothesis that this is due to abnormal cell death is probably not correct. But what is causing this abnormal brain growth? We really don't know, but there are several groups around the country right now who are examining genes that regulate brain growth. And we're very interested in this. If we could discover a gene that specifically relates to the mechanism involved in this brain growth, then theoretically you might be able to screen kids early on and actually intervene in this process. I want to turn now to telling you a little bit about early detection and treatment. Now, 20 years ago, it was very uncommon for a child to be diagnosed with autism under the age of 5. Certainly when I did my training, we never diagnosed a child until they were elementary school age. Whereas today, autism can be detected by 18 months in most cases, and there are good screening batteries that are now being used at 18 months of age. However, unfortunately, the average age of diagnosis is still 4 years of age. Why is this the case? Mostly because health professionals, pediatricians, and other people that are out in the community simply don't have the knowledge that they need to be able to recognize autism early on. People are trained to look for physical development, to some extent language development, but there's very little training on some of these social and emotional cues that are so critical in being able to detect autism early on. So we feel like this is a very important area where there needs to be more education of professionals in the community in recognizing autism. Now, we also think, because of the nature of the difficulties that I've already described to you in autism, that it should be possible to recognize autism in very young infants. Face processing, emotional processing, even a 2-month-old, when they see a still face, will respond to that face by getting distressed. So by 2 months of age, we're able to pick up on the emotional cues in other people's faces. So it should be possible to recognize autism in early infancy. But how would you show that's the case? Well, one approach that we've used is to actually study home videotapes of infants where the infants were videotaped by their parents, and then we can examine these at a later date. And in the first study, and this was done by Julie Osterling and myself in 1994 now, we wanted to show that you could recognize autism at least by 1 year of age. And Julie had the brilliant idea of studying first birthday parties. It's a great idea because you know the children are 1, exactly 1, and also there's something kind of standard about a birthday party. There's the bringing in the cake, and there is the singing and the opening of presents. And the interesting thing is there's an actual experiment in developmental psychology. It's called a social referencing experiment, and it's designed specifically to know whether an infant can pick up on the emotional cues of other people. What you do is you bring in a novel object, a very unusual object the child's never seen before, and if the experimenter gets all excited and happy, then if the baby's picking up on that, the baby will approach and be interested in that. On the other hand, if the experimenter looks fearful and apprehensive, then the babies will tend to withdraw. Well, what better novel object than a flaming cake to bring in and place in front of a young infant? So in fact, what you see in this naturalistic social referencing experiment is that a normal baby looks around to see how all these other people are responding. Of course, everyone's singing and smiling, and so they realize this is indeed a happy event. Whereas the baby with autism is focusing more on the plate and the cake. And we actually found that 4 behaviors distinguished virtually all of the 1-year-olds with autism from virtually all of the typical babies. And those 4 behaviors were, 1, looking at faces, pointing and showing, which are early gestural behaviors. We call these joint